All right, coding session time. Today we mean business. Last session we managed to call GLFW, which is pretty awesome. Calling C. I have actually seen that there's still some issues with this, but for this simple case it works. And now I did some research into, because I want to render a triangle to the window, right? We've opened a window with GLFW. Here's our window. I want to render a triangle and use an OpenGL. And the one big feature in our language that we don't have and need for that is floats. We need floats to position the vertices of our triangle, and going forward, with graphics, anything interesting we want to do needs floats. I've done a bunch of work to try and figure floats out. I don't want to spend too much time talking about it because it's a big beast, and this is probably going to be a long video to get it sorted. But I'll just say there were two different approaches I could have taken. I could have used the FPU. In x86, the FPU is, I think it's the float processing unit. That's like the old school way to do floats. But it uses this stack of registers, so you have to push values onto the stack and then perform an operation with the values in the stack and then pop them back off, and it's a bit kind of confusing and weird, and I don't like it. So we're just going to skip straight to SIMD registers. I won't go too much into what SIMD registers are yet. We'll get to that later. For now, you can just think of them as registers that can hold floats. And they're much easier to use, much more like the existing general purpose registers that we already use. So let's get into it. So we're going to add some floating point types. So if we open our grammar in a nice formatted way, we need to add some floating point types in here. And I'm also noticing that we don't have the C string in there yet. Should be a C string type. And actually another thing I'd like to do is add a CInt type. I mentioned in the last session that we're using i32 right now, but CInts are platform dependent. They might be different sizes on different platforms. So I just want to quickly make a CInt type. And we're going to hard code it to 32-bit right now, but nice to have a separate type, I think. Okay, enough talking. Let's get something done. So we have bool, boom, boom, CInt, CString, and we want a 32-bit float and a 64-bit float. There's our extra types. Cool. Actually, the one other thing we need to do here is we have this number literal, which at the moment is just one or more digits. But we need to be able to represent, so yeah, this is for literals in our, like this. But we want to be able to do something like this, right? We need to have a decimal place so we can do floats. So I'm going to take this, put it down the bottom and call it a digit, which is just, some number. Just check that looks right. Yep, that looks good to me. So now a number can be one or more digits, optionally followed. Let's close this up. So optionally followed by a decimal. And I'm going to say you don't have to have a digit after the decimal. I think in a lot of languages you wouldn't have to have a digit first either. We could do that, but I feel like it's going to be just a little bit simpler to tokenize this way. So we can always change it later. But at the moment, there's one or more digits, optionally followed by a decimal. And if there is a decimal, we can put digits after the decimal if we want. Okay, tokenization. We're already at the number. So let's do this first. So it needs to start with, I don't think we need these brackets, but it needs to start with a digit. Then we can continue with a digit or a period. But we can only have one period in the number, so I'm going to say period found. I don't know if period is the right name to use in this context, but that's what I'm going to use. So, and we'll say if we saw a period, then we'll say period found. And then, so I guess we need to go, if not period found, and decimal. So that should mean that we can only allow one decimal or one period. I keep it using different terminology. We definitely start with a digit, then we can have more digits, we can have one period, and we could have more digits after the period, but we don't have to. I think that meets our requirements. And then it's just some data types. So this should be super easy. We just add to our list of data types. Like so. Okay, so I think that's data tokenization. Parsing. I don't think we need to change parsing. I think it's basically the same. Type checking. So with type checking, I'm actually not sure what we need to change here yet. Let's start on generation. We'll probably need to come back and do some different type checking, I assume. But generation is where really things get interesting, I think. So, where is, I should really, maybe not this session, but one day I will definitely split these files up. This is getting to 800 lines. You know, it's quite a big file. Yeah, I think it might be easier to navigate if we split them up. Anyway, so what do we need to change in here? We will need to change negate, but I'm not going to worry about that too much yet. Number is where this is our number literal. This is where we really need to do something like this. So we're going to have some more lists for our data section, one for 64-bit and one for 32-bit floats, because we can't use floating point numbers as immediates. You know, currently if we look in here, see we've just got like integers that we just hard code directly into the assembly. You can't do that with floats. So we need to do something similar to what we do with strings, you know, where we have these data section lists. So I'm going to say if the data type name is F32, then let's say our F32 name, which is F32 underscore. This is what we did to copy it into our newly allocated C string, which we don't need to do here. So we need to make this new F32s list. Maybe I'll make those lists now. F32, F64. Yeah, we'll need to do more with those, but let's continue this for now. So we've figured out the name. We've added it to here. And now we want to return, I guess, the name of the variable as memory, a memory address. I think that's it. Then if we're talking about a 64-bit float, then we basically do the same thing, but everything is F64. Yeah, I think that's it. So basically, if we come across a number and we're talking about a float, then we want to reference something in the data section. Otherwise, if we're just talking about an integer, then we return an immediate like we used to. Okay, so I want to do some, before I forget, we need to sort this stuff out, these new lists. So we have like this management stuff when we're copying and closing contexts. We shuffle around these lists. So let's do that. And then up here as well, like so. And then we need to actually put these floats in the data section, right? So F32s will be F32 underscore, and we're defining a double. Now, the way we've defined it is that we could just, like in our code, we could write something like this, and this could get evaluated to a float. But in assembly, if I just did this and then had an integer value, the assembler would interpret that as an integer. So we need to make sure we have a decimal. So I think basically we need to say, like, if there is not a period, just put a period on the end. So like final float goes like that, and if index rune, I think it is, so if that's -1, that means that it's not present. And if it's not present, then we want to concatenate. Put a dot on the end. Should I extract that into a procedure? I don't think it needs to be. I think we need to do that though. Is that happy? Yes. Let's not bother extracting it right now. We've got a lot to do today. So that can be like that. So that's F64 and DQ. Okay. So I think that's basically the literals done. But now things get complicated because we're going to use just some different registers. So yeah, here we go. Register numbered. This is where things get interesting. Because now, depending on the type, we're going to return a different register. At the moment, we're just using general purpose registers. But I mentioned SIMD registers, and that's what we want to start allowing. So I think I'm going to start passing the data type and the context in here. Another thing I was thinking is that just for consistency, it would be nice to, I'm just going to always pass pointers. To these procedures. Probably not very necessary, but and now of course I create a bunch of errors. Okay, let's finish this and then we'll go through and fix everything up. I'm also, for consistency, going to do this for the named registers. Okay. All right. We need to know if it's we need to know if the data type is a float. So where do we have, was it in type checking or I think parsing maybe? No, maybe type checking at the top. Yeah, we have this numerical data types. We should have added to this. So let's add our f's and also our cint. And now I want to make some subsets. So float and signed integer. So we can compare against these lists to see with what sort of number we're looking at. Okay, these are the floats, these are the integers, and number is who knows what. Okay, so if we go back here, and float data type, I can't remember where I think it's underscore first. And we do a slice linear search, which does this stupid import, which I don't like, and I think it did here as well. Let's fix that up. I guess we're here. All right. So we figure out if it's a float, and if it is a float, we have some special handling. I'm going to copy this in here, and it'll make more sense in a minute why. And we just return something like this with XMM. Oh, that dog is going off. Hopefully it's not too loud. He really goes off sometimes. So these are the SIMD registers. There are actually like different ones. I think there's like YMM and maybe like ZMM or something, which are even bigger. But we don't have to think about it too much right now. Just think of XMM number as a register that can hold a float. And these numbers, they start from 0, XMM 0 up to XMM, I don't know how many there are actually. Whereas these numbers for general purpose registers start from 8. So if we want to be able to pass a number in here and have it just work, I think we need to assume that this number starts from 0, and then in here I'm going to say plus 8, so that for these registers the numbering starts from 8. So we're going to have to search through the file and change a lot of 8s to 0s to make sure that works. And here we're going to say byte size of data type context, I think. Okay. Cool. All right, I think that's it. And then up here, I will do this byte size of again. There's no such thing as a named SIMD register. So I think we're just gonna like have an assertion. Unsupported data type, something like that. Why is that complaining? Oh, it's not. Okay, good. All right, so those are our registers now. Before I forget, I'm going to search for 8s, and we're going to figure this out. So here, these numbered registers should be 0 and 1 now. Before we go past here, let's just add these. We need to add sizes for these. And I'm just going to put a to-do here because this is platform dependent. But I will just hardcode it to 4 bytes for now. And these are the floating point ones. Cool. Those 8s are fine. That should be a 0 because the 4th, it's a register number. This is also a register number. We'll come back to this because we also need to change the parameters, but I just want to take care of these 8s for now. And maybe I'll get rid of those also. So this is also 0 and 1. Change those parameters later. Generate expression. This also has a default register number, so we'll put that at 0. What else do we have here? I have some 8s in here. I think this one is like a size or something. That's a size. This one is an offset from RSP. Fix that up. Any more 8s? Have some 8s down here, but I think in all these utility functions, we're probably not going to have an issue. Okay. Cool. So we did the 8s. So now let's cruise up here. We'll go up the file, and anywhere where we have register, right, we need to change the parameters. Maybe I'll just grab those parameters. Where were they? These ones here. Okay, so when we copy to a register, I think now we need to supply this info. I think this copy also is going to need to change because we can't just use move everywhere, but I think we can get away with just leaving that for now. I'm sure we'll get an error later and then we can fix it. So these guys need registers. This is the call. So this here is actually a pattern that we repeat in a few places. It's kind of like it's kind of like copying a stack address. So where's all of our copies? I might make like just a copy stack address procedure. Does something like this. Needs a register number. I should really be using some sort of sized int. I don't like using these unsized ints, C-style ints. So we need a file, a register number. We also need an offset, which will go here. I think that's it. But now these are not the right parameters, right? We need a data type, kind of like up here, we need a data type and a context. So let's put them in there. Well, the data type, okay, so here we've got an address size. So I think I'm just going to make like a global data type, which is, that already has context. So that needs to be data type. Yeah, I think I'm just going to make like a convenient, it's like a, it's kind of like an unknown reference, which is a data type. And I'm not going to give it a name. I'm just going to say it has a length of 1 and it is a reference. Yeah, that's why it's unknown, because it doesn't have a name. But that should be enough for like when we come to here, just to put it in here. Yeah, like that. So then we have this copy stack address which I think we can use like here. So we'll just say copy stack address, takes in the file, context offset of 0, and what was the other one? Register num, like so, and then okay. It just seems to randomly like come up with different errors at different times, whatever it feels like. Oh, and this needs to return, right? It needs to return a location. And this will need to be byte size of. Okay, I think we're getting back into business now. So I guess that's just like that now. And param byte size. Instead of param byte size, we just put these. We don't need to get that. I think that should be that. Okay. Okay, we're getting there. Here's another, see, this is that same pattern. So this is copy stack address. So file context. I think it was also an offset of 0, right? Yeah, offset of 0. Here's another one which also has an offset of 0, so we can just copy that in there. This one has an offset of variable position. So let's put that there. Okay. We're just, so address size. If this is a reference node, the data type should be a reference. So we should just be able to put the node data type in here, I believe. Let's see. If we get an error, we get an error. This is the data size of that. So I think we can just go boom, boom, boom. Here, it's the size, it's address size we've used explicitly. So when we're dereferencing, this should be a memory address. We can only dereference memory addresses, right? So if that's a memory address, it should, but the dereference node will have a different size, I think. So I think we're just going to say unknown reference for this one. Let's see, I'm kind of winging it. We have an error down here. Okay, copy to non-immediate also needs to use these. And byte size of. Okay, now we can go back up here. We'll skip past here for now because this part this is where we really need to do a lot of work soon. Figuring out the binary operations with floats. That's where a lot of the assembly really changes. So here, I guess we just want this data type, and we need to be careful sometimes because in some procedures there will be a different context object, right? So we need to be a bit careful. But that should be that. What's wrong with that? Okay, copy. Oh, because we don't have that anymore, so that's byte size of these guys. Okay, let's go up here. So this is, yeah, see here we've got 4 context. I hope I haven't messed up and used the wrong context in some other places. Probably need to use a pointer to it. Like scope, for instance. I don't think we had to change anything there. Okay. Like so. I think it should be happy now. All right. So I think that's all of our kind of copy stuff, or all of our handling of registers should give us a correct register now. But now what I want to do is basically copy. Whoa. Okay. I messed that up. Where were we? Here we are. So I want to basically copy this and call this signed integer. And we're going to have different versions for different integers. I think this stuff we will not have in here. And instead we'll pass it in. So we need to have like left-hand side location. Right-hand side location. Result byte size and operand byte size. But no, this needs to have the data type in the context. So let's say operand, data type, and result data type, and those are in fact data types. Okay, so let's just make sure that this all makes sense. I had been thinking to split it out into two separate switches. I think I'm going to do that now. So I think I want to make like, and maybe in type checking, I'll make a list. So this is like a, or let's say, I don't know where to put it. Let's just put it here. Comparison operators, which is a list of AST node types, well, a slice, I should say. And then we just go like this. Whoops, pressing the wrong button. Okay, that seems happy. Comparison operators. And I think actually in type checking or somewhere we already do, like if we go to expression, yeah, here. See, this is all the, those are all the comparison operators. So we can say like slice.linear search. Yeah, this is kind of why I wanted this to be in a slice, just so we could do something more concise like this. And now I want to do this also here. And then I want to take this, put it in here, and I want to take out the arithmetic, so it's just the comparison stuff, because the comparison stuff is a little bit different to the other stuff. See, all of it starts with this. These two lines are the first two in every single one. So I'm kind of thinking like, why don't we just put these here like this? And then we can like reduce these down to just one line. That feels nice. And we'll just say that's compare. I don't like this dest naming, so I'm going to say result location Yeah, that's why I see I already named these left-hand side location and right-hand side location. So, but because this is a parameter, I think I'm going to have to say like this, give it a new variable. So we're comparing the left-hand side and the right-hand side, making sure that left-hand side is in a register because it needs to be. Or that's simpler that way. It's simpler that way, I'll say that. Need to do this, I think. Is that it? Yeah. Then we do our then we set the Boolean in here. Okay, and we return the Boolean. Cool. All right. Otherwise, let's cut these out of here. So the other option, see, these are a bit different. Like here, we're saying copy the left-hand side into this result thing and then return it. Whereas here we're saying, use the right-hand side is what we copy into and then copy into the result. So result is always going to be, result data type like that. I guess this one should be operand data type actually. Because this specific case in here, if we're doing a comparison between signed integers, the result data type is Boolean, but the operand is the integer. So they need to be correct. These cases, the two data types are the same, so it's not such a big deal. Let's say left-hand side location, right-hand side location. Actually, that's probably going to need to do that as well because we can't reassign. So result data type context. I'm just going to use the result data type everywhere because, in this case, the result and the operand data types are the same, so it doesn't matter. Okay. Okay, I'm kind of tempted to put this down in here and this one. No, let's leave it how it was. It's like that. A lot of these will override it, but that's fine. And then the right-hand side location, like so. Where's the left-hand side location? Here we go. So I think that should do the trick. That should be our signed integers sorted. So then back up here, I'm going to call that location as well. And this is, well, these data sizes, do we need these? I don't know that we do. So now I'm going to do some more checking of what kind of data type it is. Slice.linear search. So I guess what we do want is like I want to do this because I feel like it's a bit clearer, an operand data type, and that's what we want to check. So if the operand is a float, then we want to go into the float version. Let's go like this. Which does not exist yet. And if it's a signed integer, then we go into the signed integer. Oh, yeah, so that should be float. We want a float version of it. And also, we can't forget booleans. The operand could be a boolean. So if we're talking, if we're talking about a boolean, we need to do this, and we'll make a bool version. And then down here, let's assert, similar to this, just failed to generate expression. That should be equals equals. Okay, so I think let's make the Boolean one first, because that'll be nice and simple. Yeah, so Booleans, we cannot do any of this. So we don't need to do that. Also, we can't do any of these. It's just equal or not equal, that's it. So is that basically it? I mean, here, I think we don't actually need a result data type because all the data types are going to be the same. So I think we can just do that. Yeah, I think that's it for bools. So we just take out the result data type. So we need to actually create these. So result data type is just no data type. And that should be the name actually that we're comparing against. Okay, so now it's just the float that we need to do. This is what we actually wanted to do. All this was just preparation to get to the float. So here we go. Floats. How do floats work? Well, if we're doing a comparison, there is a different operation. It's called com_i ss. So com_i is like comparison. S means, I think it stands for scalar. Because the thing with SIMD registers is the whole idea is you can put more than one value in a single register. You could have like 4 floats, 8 floats, or even more depending on the size of the register. But at the moment we're just dealing with single ones. So S is for scalar, or a single value. And this second S is for single precision. I think I'm going to make like a little helper function for precision. It's kind of like one of these. Whoops. Precision. Yeah, we can just base it on the size. It's either 4 or 8. So it's either, so that's called single precision, that's double precision when it comes to floats. 4 bytes is a single and 8 bytes is a double, and we'll just say unsupported to precision otherwise. So where were we? That's the bool. So we were here. So this here, I want to put a %s, and then we're going to plug in our precision, which is uses the byte size. And the byte size needs those two. Yeah, and then just like normal, you specify your two things. I'm making sure that this one is a register on the left-hand side. This one could be memory, just like before. And actually, there's also a variation called ucom, which I'm going to use. I don't really know these operations very well, but apparently ucom handles nan, not a number, better. I don't know. Let's see. Okay, and the other thing to note here is that we were using L for less and G for greater in these operations. That terminology is specific to signed integers. Unsigned integers and floats actually use the terminology above and below. So instead of less, it's a B for below. Instead of greater, it's an A for above. So that's below, that's above, like that. So maybe, I think we're going to need to use this precision in a few places, so I think I'm just going to put it up here. Precision, because we need to change these operations to, basically we need to add this scalar, and then this will evaluate to the precision. So we need to do that. It's not imul, it's just mul. Not idiv, just div, and we don't need all this crap. Division is much simpler. Very happy. Okay. Okay, so we want the precision to be added to all of these. Boom, 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 boom. And yeah, so here the result location is a bool, but here it is not. So here we actually copy the left-hand side to the result location. And then, yeah, then we do it like this. This makes sense. So in here, I think it does make more sense to put this result location in here. Because here we do it differently. But I think that's basically it, right? Yeah, so it's happy. So I think that's all the binary operations done. I feel like we've probably missed some stuff and something's not going to work. Let's see what happens if we run this. Wow, we don't get an error? Oh, well, we don't use floats anywhere. That probably has something to do with it. So if I go like that. Okay, that's more like it. So line 36 is an expression syntax error. 36. Okay, so this is, I said that we can't have floating point values as immediates, and it looks like the code still wants to do that. It's using our nice, it's using our correct registers. It is doing a move. Actually, that was something that also, because this also needs to be move SS. So that's something we need to change. And we need to make sure that it's not doing that. Let's do this move first, because I know how to do that. That's in the copy. Yeah, so I think the copy needs to know this stuff also. So let's go like that. It's probably going to create a whole lot of errors. But maybe before we get to fixing those errors, let's just implement what we need to implement in here. So these are all the cases. Memory to memory, I think, is like totally fine. Nothing needs to change. There's a few places where we need the size. So let's get the size maybe here. Byte size of. that should be happier now. Yeah, so register to register, or if either of them are register, that's where we need to do our move, like SS, or actually it's a precision, which also needs the byte size. Well, it depends on the data type, right? So this is where we need to check the data type. And if it is a float data type, then we do this. Otherwise, we do what we did before. So otherwise, we take that off again and take out the precision. So yeah, we're just adding this little bit if it's a float, basically. This should be invalid because floats can't be in immediates. So maybe what I'm going to do is I'm going to take this out here, put that there, and then I'm going to say, put an assertion in here and say it cannot copy float from immediate. Okay. Yeah. All right. I think I'm pretty happy with that. So now I think we need to like change the parameters to a lot of these things. Yeah, we just need to, anywhere where we have copy, we need to add the correct parameters. And that's basically it. Data type context. Is that happy? Should be happy, right? Oh, because we need to take the byte size of out. We're replacing it. Okay, that's nice. Not too many more parameters. So this copy here is also address size. So I guess this is the unknown reference thing. And here also. Yeah, I think we just use unknown reference. There might be a better way to do it, but. And here, actually, we know what the type is. This is where we're adding the length into our string object, which we know is an I64. So I can go I64, 1 false. That's the data type. And up here, so we know that's the data type and that's the context. And same here. Is that it? Okay, let's try and run that again. We still get the same error because that's still wrong, but now we have move SS. Okay, cool, making progress. So why is that a 1.1? Well, when we do generation, yeah, here we go, generation of a number. If we're getting to here, it means that we don't have float type information. And this is exactly where it happens. So if they're unknown number types, so this is, we're doing this comparison between 1.1 and a register. So I believe we're talking about this here. So in this case, this is a number, this is an F32. Which would coerce, up here, it would coerce into an F32. So it wouldn't go into here. And the right-hand side, the 1.1, would just stay as number. Huh, I think that was an issue. that we never fixed. So maybe we need to say else, just take whatever data type it is and we push it down. Is that safe? Are we going to override some other stuff? I think we are. Like, what if we come across a reference or something, you know? Like we might come down. So maybe we should make sure that this only ever propagates to places where it has number. Because if we propagate down where there was something that's not number, like F32, then it might go down to a node where it should actually be an F32 reference because there was a dereference happening, and it'll override that with just F32 and cause issues. Let me try and show what I mean. So in here, say this is where we are. We're at this assignment, and we're evaluating, and we see that this side evaluates to F32. This is F32, and this is just number. Yeah, so maybe we're at this add. We have this on the left, this is on the right. And then we see, okay, this is F32, this is number. So this has evaluated to F32. So we go into here, and then we say, okay, just throw F32 everywhere. So here will become a single F32, which makes sense. But this will get overridden just to a single F32, where it should be a single F32 reference, I think. And then down here should be an F32, a reference to an F32 array. So, oh yeah, so this should be an F32 array actually. And this should be a reference to an F32 array. And it's just going to override all of these with just an F32, which is going to cause havoc in generation. So maybe I'm just going to put in here, like, it's a bit weird, but if we're not dealing with number, then let's just return. We should only ever overwrite number data types. And maybe that means that we can simplify this now. I think we just leave it as is. I think we'll change this to a float because we don't know. It might be a float. And I can't be bothered checking them all. Checking the tree to see whether any of the literals are floats or not, and then deciding to be float or integer based on that. That's what we could do, but I can't be bothered. Float should cover everything. So let's try that. Unsupported operation size. Okay, so what's happening here? We're trying to do a copy from the immediate 1 to the stack. Okay, and the issue is that the data type is just number. So I think this has not worked very well. We should not see anything that is just type number when we get to generation. everything should be properly typed. So somehow we're not getting that. Could it be that? So the expression, the expression is just a 1. The expression is just a 1. Then when we go back to type checking, this is actually up here, I think. So we go into type check expression, but then we just go straight into primary. We get back a number, which makes sense. Then we coerce it with the expected data type. We should give it a proper type. And if it was number, then we should be overriding. Right? So this expression, no, this is a number, which is 1. This is kind of, I think this is where we were. It has a number data type. So we should go into here, propagate, and the data type name is number. So we should go. What? The data type name is number. So why is it going into here? I8. Okay, it should be the node data type. If the node doesn't have a data type of number, then it should skip out. Yeah, because that data type, the data type that we're propagating should never be number. Like, there's no point in doing that. Okay, let's try that again. Invalid combination of opcode and operands. Okay, let's have a look. 790. Neg. Okay, we didn't handle neg yet. So we need a different operation for negation of floats. So in our generation of primary, we should have negate here. And see, we just go neg. So actually what we want to do is, depending on whether it's a float data type or not, we use a different operation. Float data types, like so. And the operation, that's right. I did my research with Grok before this. So we'll have to find the, I think it's called like X or P. Let's go to the top first, X or P. Okay. So yeah, we have to use this X or P, and there's an S and a D. That's the different precisions. So we're doing an XOR with the float, our float value, and this mask thing. And this mask just masks to only the sign bit. So it effectively flips the sign bit. That's the idea. So we need to have these sign masks defined, and then we need to do an XOR P between, and these have to be registers, I think. Yes, see, it's saying you cannot directly XOR with a memory operand. You can't do this, which is what we do. You know, normally we have like, you know, the move SS and the icon. These are just using a register and, well, we have to change this, and a memory. But you can't do that with these. So we need to define this and do this operation. And this is the 64-bit one. Here's the 32-bit one. They have different masks. Okay. So XOR P %S, and that's the precision, which needs the byte size of, we should take these two. And it needs two operands. So the first one is the register. We've put the first one in the register. And then the second one, so this is like the sign mask, is the other operand. And it needs to be in a register, so we're going to copy, I'll just say copy to register. I think that's easier to use. Not the primary dest though. It's a memory address, which is F32 sign mask. I guess we need to differentiate between F32 and F64. So it's like the data type name followed by underscore sign mask. And I'm going to create a memory address from that, copy it into a register. And then we operate on that register. I think that's right. But we need the sign masks. The sign masks need to exist. So in our data section, we need a DD and a DQ. The sign mask. Don't need these parameters. And then we need to just take those values. It's these two for single precision and for double precision. Okay, so now we have our sign masks. Yeah, I need to do something about this. This file's getting pretty hard to navigate. And we've referenced them here, put them in a register. Let's see what happens. Okay, negate is failing, but things are working. That's not right, because we're putting the float in here and then we're just like immediately overriding it with the sign mask and then doing an XOR of itself. That's not what we wanted. So I feel like this is a bit hacky and hopefully it doesn't cause any issues, but let's just put register num +1 for the sign mask. Oh. Yeah, so the sign mask goes into MMM6, then we XOR with MMM6. And we got a window, which means that it worked. And so the reason that in tests now, it's using all this float stuff, even though we didn't explicitly say that we're using floats anywhere here, is because now in type checking, remember we did this. So if we come across a comparison operator and there are nodes below it that are numbers, we make them floats. So an example of this is here, this negate that we just looked at. This is the negation assembly. So because we have this comparison operator, the left is this and the right is this, and they're just numbers. So now we're evaluating those as 64-bit floats. So it should be the D version, isn't it? Yeah, D for double, because they're 64-bit. I'm actually really surprised that these work. Because I thought there would be like a lot of issues with floating point. I don't know if it's, I can't remember the term, like non-determinism or imprecision. But you know, if you have a float of say 6, it might actually evaluate to like this, which means that this equality check is not going to work. So the fact that all of these tests are actually passing is I'm kind of surprised, to be honest. Dog's going again. Not good for videos, having this crazy dog in the background. But are we done? Let's put, we made that CLion type, so let's put it in. I think we need to do type checking as well. Is it type checking? Yeah, so that's CLion. I think we're done. We don't really have a way of printing out floats. So yeah, I think in the next video is when we're really going to figure out whether this is actually working properly, because we're going to take floats and actually do things with them, render a triangle hopefully. And so if the float values are wrong, we're not going to get a triangle, basically. So hopefully it's right. Yeah, here we go. 1.1, 1.1. And in our tests, yeah, we've put this decimal on the end. This is like super inefficiently storing these floats. Like, look how many duplicates of 1 and 2 we have. And they're all DQ, right? Like, I mean, you could have a 1.dd and a 1.dq, but these are all, like, this is just a waste. So we could deduplicate those. We could potentially even deduplicate the strings if we really wanted to. That would probably actually be a good idea, because they take up more space. But we're going to leave that for now, because I'm just like, I'm quite happy, and I'm actually like, I can't believe that's actually passing all the tests. We didn't turn off the tests, did we? No. So yeah, stoked. Okay, we have floats. Next stop, OpenGL triangle, which I don't think is going to need much more language features actually. Maybe a tidy up of our, like, we can implement this and some things like that. Okay. Yeah. Thanks for stopping by. Have a good one. Ciao for now.